Hello, Mr. Sorrentino here again, presenting another one of the videos from Math 31, which in this one is going to deal with section 3.4, solving rational equations and radical equations. So rational equations are ones like you see here in example 1, where I have expressions involving a variable in the denominator, recognizing that when we solve an equation, we want x or whatever the variable is in the numerator alone on one side. And we're going to deal with radical equations, which means we're going to have solve equations where I have the variable underneath of typically a square root sign, although they could be other roots as well. But we're going to focus our attention mainly on square roots for this course. So going to the rational equations. Now, the reason why this is presented in this chapter, because we dealt a lot with quadratics here. We're going to end up with situations where I do have quadratic equations as a result of the work I do on these. So that's kind of the context and why it shows up in this chapter. The one thing I want to keep in mind, and we're actually going to have an example that focuses on this, is that these two types of equations, your rational equations and your radical equations, are ones that produce possibility for extraneous solutions. I had mentioned this in passing in another one or two of these videos before this one. An extraneous solution is a solution to an equation where I do everything algebraically correct, but either because of the circumstance I'm presented with, or any other things I may have had to have assumed as I went through the process of solving the problem, just in the end produces an answer that just doesn't make sense to the context of the problem. So it's actually just an extra solution. I just disregard it once I realize it doesn't make any sense. These two types of equations are noted for having those quite a bit. And we can usually recognize them pretty easily once you get the idea of handling it. So let's take a look at, these types of equations. What can possibly produce the extraneous solutions, and how do we go about, solving these equations? When we solve rational equations, the primary principle that we're going to be using is a procedure known as cross multiplication. I mentioned this also before in a previous lesson. But when I'm using cross multiplication with rational equations, which basically means if I have an equation where I have a fraction equal to another fraction, that's important. A single fraction on the left of the equal sign equaling a single fraction on the right of the equal sign, then this is also true. I could multiply across the equal sign in a crisscross fashion. So I could say as a result of this, AD would equal BC. Now when I go through and do the procedure for this, A, B, C, and D could have one or two or even more terms in it. So I have to be aware of that as I do it. So the first one, I do have a single fraction on the left, I have a single fraction on the right. It's already set up to do cross multiplication. So if I wanted to solve A, I would do 2x times x plus 1, and that would equal 5 times x plus 7. One of the first things I want to do when I have a situation where I have x's in the denominators is get them out of the denominator when I'm trying to solve them. And cross multiplication allows for that to happen. Now I want to solve this equation, which means I'm going to need to do some simplifying. On the left, I'm going to distribute a 2x, so I'm going to have 2x squared plus 2x. On the right, I'm going to have 5x plus 35. Now we can see that this is a quadratic equation. I do have a degree 2, and it's a non-basic one because I also have x terms in here that are going to stick around. They're not going to cancel out with anything. I can have some cancellation occur and get down to one term that only has an x in it, but I'm not going to make it disappear altogether. So At this point, I would have to make a decision, which method do I eventually want to use? Do I want to use factoring? Do I want to use completing the square, or do I want to use the quadratic formula? Now, under a lot of circumstances, when you're doing these equations, you could expect rational solutions, and we're expecting real number solutions. So another thing that they don't always say outright, when I'm solving rational equations and radical equations, I am solving them for real numbers, whereas with quadratics in general, it is possible for me to solve them for, any number, real or non-real. So, um, I'm just going to choose to use the quadratic formula for this. So I'm going to get this equation set equal to 0. So I'm going to subtract 5x from both sides, which will give me a minus 3x. I'm also going to subtract that 35. And using the quadratic formula, x is going to equal negative 3 plus or minus the square root of negative 3 squared minus 4 times 2 times a negative 35 all over 2 times 2. So 3 plus or minus the square root of negative 3 squared plus minus 4 times 2 times negative 35 becomes a 289 all over 4. The square root of 289 is 17, so I'm going to have 3 plus or minus 17 over 4. 3 plus 17 is 20, divided by 4 is 5. 3 minus 17 is a negative 14. And a negative 14 divided by 4 is a negative 3.5. Now, as we start doing this more and more frequently and we solve more rational equations, there's also something we tend to need to do first before we even get into all this. All of this work I've done and shown here is based off of a premise. And the premise is that 2x over x plus 7 as well as 5 over x plus 1 both exist. That's a lot to say. I'm assuming existence beforehand. Anytime I have to make an assumption like that, if I have to assume that that both of these expressions produce values that exist, and there is going to be a possibility that they're going to exist and have the same value, those are some major assumptions. And when I make those kind of assumptions, that's what causes there to be the possibility for extraneous solutions. For these to exist, the original functions, x could not equal negative 7. And x could not equal negative 1. Those would be solutions that I cannot have, because if x were to equal negative 7, the left-hand side of this equation would not have existed. If x were to equal negative 1, the right-hand side of that equation would not have existed. And therefore, for these two values, x cannot equal this. But when I go through this process and I end up turning this rational equation into basically a quadratic equation, which has no restrictions at all, these solutions could be possibly come out of the quadratic version of this. And because of that, that's where the extraneous solutions would possibly come from. And therefore, there will be times when you solve equations like this and you get your answers down here, you may find out, well, wait a minute, one of these, these answers here don't agree with the answer what I have up there. This one does. Neither one of these is negative 7 or negative 1. These are both credible solutions. I should still probably go back and plug them in to make sure they work. Plugging 5 in, I get 10 over 12 on one side. I get 5 over 6 on the other. Well, 10 over 12 equals 5 over 6. Those are the same fraction. And I can do the same thing with the negative 3.5, which I'm not going to get into right now. So those can be done and verified that those are solutions as well. But, if I had to, if I end up getting a solution that went against this, I'd have to throw it out. So that's where the extraneous solution comes from, because as I work on this equation and I go through the solution process, every step along the way after this, after the initial equation, I'm assuming that both sides of this equation existed. You know, and so like that's a big assumption, in this case, because there are instances where any one of these two sides don't exist. When I'm dealing with a regular quadratic equation, there is no place where, where the function does not exist. It's going to produce a number no matter what I plug into it. Not necessarily the case for rational equations. So B, slightly more challenging. The reason why B is slightly more challenging is because I am not ready at this stage to handle cross multiplication. I don't have a single fraction on one side equaling a single fraction on the other. I do have a single fraction on the right. That's good. I do not have a single fraction on the left. So for me to get a single fraction on the left, I have to find common denominators. So, and one of the things when you deal with these, don't be in such a hurry to necessarily multiply things out right away, because if you do, you're going to end up getting functions that might go beyond quadratic, and we haven't talked about those yet or dealt with them yet. So, if you're getting things that have x cubed showing up, or x to the fourth power, x to the fifth power showing up, those are going to be on the nasty side, and you're going to have some issues with that because we haven't talked about handling those yet. So what I'm going to suggest to you, that if you start seeing those show up and you're trying to solve an equation where you have an x to the third or higher, you might want to consider maybe doing some other manipulations to make that not happen. And it is possible in many cases. But for this one here, I want to try to get a single fraction to be on the left so I can cross multiply with the one that's on the right. So I'm going to look at these two. This one has a denominator that's actually 3 times x plus 2 minus 1 over. And in these, this is where it comes handy to be able to do some factoring. Now, differences of squares, if I have a difference of squares, and this goes back to, again, some of this factoring stuff are things that, we're assuming you do come into this course having had in the past in previous algebra courses, and that you remember them somewhat. Difference of squares tend to be a situation that's easy to factor. And you're going to see them come up enough, and there are going to be situations that you should also be able to factor, whether you use the AC method or another method you learned in high school. And the values won't be as horrific as some of the ones you may have seen in the quadratic section, where it came off better to use either completing the square or the quadratic formula. Difference of squares are pretty easy to factor because generally if you have something that's x squared minus a squared, where you have the difference of two perfect squares, I'm just going to have x, a, and a, basically the square root of each one of those terms. One's going to have the plus and one's going to have a minus. So x squared minus 4 squared is going to be x plus 2 times x minus 2. And for reasons we'll get into momentarily, leave a little bit more room over there. For me to get the left-hand side to be something I can make into a single fraction, I'm going to need to be able to carry through that subtraction. For me to carry through the subtraction, I need a common denominator. So when I look at this, both denominators have an x plus 2 in common. I can see that. However, the one has an x minus 2, while the other one doesn't. The other one has a constant of 3 being multiplied, while the other one doesn't. So for me to get a common denominator, I'm going to multiply this by 3 over 3 to get the 3 times the multiplication of 3 down here. This one I'm going to multiply by x minus 2 over x minus 2. And so what that's going to give me is I'm going to have x minus 2 over 3x plus 2 x minus 2 minus 3 over 3 times x plus 2 x minus 2, which equals 3 over x plus 2. I haven't done anything to the right hand side because I already have a single fraction over there. Now I have a common denominator I can carry through the subtraction. So x minus 2 minus 3 for the numerators is going to be x minus 5. 3 times x plus 2, x minus 2. So now I have it set up. Now I have a single fraction on the left and I have a single fraction on the right. Now I can carry through the multiplication, the cross multiplication. So I'm going to go with this crisscross. I'm going to have x minus 5 times x plus 2. And that's going to equal, and when I do this crisscross, I'm going to have 3 times 3 x plus 2 x minus 2. So now I'm going to carry through the multiplication. So on this, on the left hand side, I'm going to carry through the foiling, and I'm going to simplify as I move along. So I'm going to maybe skip a step as we do this, but make sure you can confirm that you get to the same point. I'm going to have x squared minus 3x minus 10. Here I'm going to have 9. X plus 2 times x minus 2 is kind of reversing what I had up here for the difference of squares. That's going to be x squared minus 4. Scooch down a little bit to give myself a little bit more room. So now I have x squared minus 3x minus 10 equals 9x squared minus 36. I have a quadratic equation here. I do want to get it, solved. So I'm going to set this equal to 0 because, again, I like the quadratic formula because it's the easiest, and I'm pretty good at factoring and recognizing whether or not it's going to have factors or not. So I can usually do that pretty easily, whereas completing the square, although I know how to do it, it usually has much more heinous numbers to deal with. This is going to have a leading term that's not 1, which causes even more headaches, so I'm not going to give myself the complication of that. So I'm going to subtract the x squared from this side and this side. I'm going to add the 3x to both sides. And I'm going to add the 10 to both sides. And what that's going to do for me is, now I'm going to rewrite everything on the left-hand side with the x's. I'm going to have 8x squared minus 33, or plus 3x minus 26, and that's set equal to 0. I'm not going to use factoring with this because, when I see like 8 times 26, it's going to produce a lot of potential factors that I have to go through to figure out, what should come out to be a difference of a positive 3. I don't really want to do that, so I'm just going to use the quadratic formula. So again, give myself a little bit more room here. With the quadratic formula, I'm going to say, well, x is going to equal negative 3 plus or minus the square root of 3 squared, which is 9, minus 4 times a, which is 8, times c, which is negative 26, all over 2 times 8, which is 16. So 9 minus 4 times 8 times a negative 26 is 841 over 16. The square root of 841 is 29. So x is going to equal, well, negative 3 plus 29 is going to be a 26 over 16, which would become basically 13 over 8, which is the same thing as 1.625. The other answer is going to be, well, negative 3 minus 29 is a negative 32 divided by 16, which is negative 2. But wait. These are the two solutions I have, but again, all of this work that I did, every bit of it was working under the assumption that each of the three original rational expressions were producing values that exist. And the fact of the matter is there are some values of x where that would not have happened. For instance, when I go back up to here and look at the originals, 3x plus 6, if x equal negative 2, make my pen, if x equal negative 2, the first fraction wouldn't exist, neither would the one on the right-hand side. Neither would the second function. I mean, the second expression, 1 over x squared minus 4, would not have existed if x equals negative 2. Also, x couldn't be a positive 2 because that would cause this fraction here to also not exist in that instance. So for me to do all this work, I had to have been working under the premise that these were existing, which meant it couldn't be any of these two values. Why is that important? Because x equaling a negative 2 was one of the solutions I came up with. And although I said I was going to be dealing with that more in a later example, it came up here. This is what we would call an extraneous solution. Now, I could have possibly taken care of that earlier, because right at this stage here, I could have made this a little bit more simplified and not have to even deal with a quadratic equation if I recognize, well, both sides of the equation had an x plus 2 there, which meant I could legally divide both sides by x plus 2, canceling that, and that would have given me, essentially x minus 5 equaling 9 times x minus 2. And if I work my magic here, negative 8x by subtracting 9x from both sides, adding the 5 to both sides would give me a negative 13. X would have been that 13 over 8 regardless. And I would have gotten that one and only answer. And the extraneous solution would not have shown up at all. So if I handled it differently, I could also account for the extraneous. Another thing that I could possibly, why it's important to identify what could possibly be extraneous solutions, is you can see, if you see that kind of cancellation that could occur, so well, I'm just going to cancel, it's going to make my life easier because I know that x equaling negative 2 would make both sides equal, but it's also an answer I can't have. And as a result, I need to just get rid of them immediately. So what you see also on your page, and I'm not going to show the calculator stuff because I've shown it in similar instances with simpler functions. It's kind of the same thing. Basically me showing here, how to use your calculator to using either the intersect command or the zero command to come up with the answers to this. You can see I got the one answer for this one because you see it was only one place where they actually agreed, and the two intersections on this one, so 5 and -3.5, which I got as answers before as well. So the calculator could definitely back these up as well, but eventually you have to get to the point where you don't use the calculator, um, because during the file you're not going to have it. Um, but as I mentioned, the extraneous solution, even though I was trying to avoid this when I made up these examples early on, I still ended up coming up with an instance where I had one. It's hard to avoid it because a lot of times these type of equations have extraneous solutions. Radical equations even have more of them because because of the way the square root symbol works. So there's a great possibility for those to have extraneous solutions as well. So let's have a look at some examples of those. Now, as we deal with radical equations, we're going to use this idea of the principle of powers along the way. So basically, if I know I have two things being equal to each other, if I raise them to a power, it's also going to be equal. So if I know that the square root of a plus 9 equals a positive 4. Now, first of all, one of the things to be on the lookout for a possibility of extraneous solutions, and it does come up every once in a while. Remember that a radical, a square root symbol, means the positive square root only. So if I have a radical equation set equal to a number that's not positive, automatically there I'm going to say, well, there is no real solution for this. I just have to stop right there. So, because I'm not going to be able to apply really this radical and be able to come up with a negative answer, unless I'm talking about non-real numbers. But again, when I'm dealing with radical equations, where the assumption is we are dealing with real numbers only. The reason why it's important to have that principle up there is that's how I mainly am going to solve radical equations, because to get rid of a square root symbol like that, I have to square both sides. And when I square both sides, I'm going to have a plus 9 equaling 16, and then I'm going to subtract 9 from both sides, and I'm going to get that a equals 7. Pretty straightforward, and it does work. However, we talked about radical functions before and things of that nature. All this work I just shown, even though it wasn't a whole lot of it, works under the premise that both sides of this equation exist. 4 exists, that's easy. It's a number, we know it's defined, we know what it is. The square root of a plus 9, however, doesn't always exist. There are values of a that makes it not exist. So when I start the problem, or when I realize that once I got an answer, I have to realize that all of this work done was working under a premise that, in this case, a had to be greater than or equal to -9. Because if it wasn't, the square root would have a negative underneath of it, and I wouldn't be able to solve it in the real number system. For the reason that, whereas with the rational equations, I would have maybe 1 or 2 numbers for which it didn't work, or possible extraneous solutions, radical equations have intervals of numbers that won't work. Anything, anything that's under -9 is not going to be an answer. And so if it comes up, which it didn't here, but if it came up, I had to get rid of it immediately. It has to go away. So that's why radical equations will often have situations that have extraneous solutions as well, because for me to carry through the work means that I'm assuming that it's anything but any number that makes any of these radicals not work. Situations where you have a square root of some quantity equaling a number, they're typically going to be very safe. You're not going to really have any extraneous solutions on them. When you get to situations like B and C, that's where they start becoming more of a possibility. Case in point, the square root of 7x plus 4 equals x plus 2. Now I have an x that's not underneath of a radical, and I have an x that is underneath of a radical. I can't combine them in any way. I can't like subtract x from both sides or anything like that and make the combine with what's under here, because all of this is basically assumed to be under a grouping symbol. This is also acting as a parenthesis. And we all know that parenthesis, I can't move anything from outside of a parenthesis inside unless it's all I have is a parenthesis. This square root would have to have been dealt with and taken care of and made to go away before I could even possibly combine any terms and things of that nature. So, now the thing is here, we're working under a premise that, this is possible, okay? 7x plus 4 has to be greater than or equal to 0 for this to have any kind of solution that I could possibly find. Which means that 7x has to be greater than or equal to negative 4, which means x has to be greater than or equal to negative 4/7. Anything that's under 4/7 will not be an acceptable answer. But I am going to use the fact now that I'm just going to work under the assumption here that, this has, that I'm only considering values of x that could exist. So I'm going to square both sides to get rid of that radical. On the left hand side, pretty easy. It's 7x plus 4. The right hand side, and of course the x plus 2 square, which I showed here, is going to equal x plus 2 times x plus 2. Sorry for the quick edit on that one. So I want to carry through and FOIL that out. So the left hand side, I'm going to still have 7x plus 4. On this side, I'm going to have x squared plus 4x plus 4. I want to get the set equal to 0, because again, I don't usually use completing the square a whole lot. I usually use either factoring or the quadratic formula. So I am going to subtract 7x from both sides and then subtract 4 from both sides. So I'm going to subtract the 7x. That's the two terms that I'll combine. I can subtract the 4. And so I end up with an equation that is x squared minus 3x. The 4 and negative 4 cancel. That's going to be set equal to 0. I'm going to actually use factoring for this because without a c term, it's pretty easy. I'm going to factor out the x. X times x minus 3 equals 0, which means x is going to equal 0, or x minus 3 is going to equal 0, which means x is going to equal 3. So my two solutions are x equals 0 or x equals 3, because both of them fit into this. They're both greater than or equal to negative 4/7. And that works. This makes this, all true. If I had a value that was like negative and below negative 4/7, I'd have to have thrown it out. So moving on to the next one, C. C is a little bit more complicated. If I could actually get to it. No, it's over here. There we go. Here I have two separate radicals being added together, and I'm saying they're equal to 9. I'm not able to combine them through addition. If there was multiplication, I could make that the square root of x plus 7 times x plus 6, or the square root of x plus 7 times x plus 16, but I wouldn't be able to do that through addition. I want to clear out those radicals. It's going to be a little bit more problematic because of the fact that, really the only thing I could do to this to get rid of radicals is to square, but sometimes students, they square this incorrectly, because when I square both sides of this, I'm squaring two terms over here and one term over here. So the right-hand side is pretty easy. The left-hand side, I have to think of it as I'm doing x plus the square root of x plus 7 plus the square root of x plus 16 times the square root of x plus 7 times, oh, getting a little ahead of myself there, plus the square root of x plus 16. And so I'm going to need to do these two together, multiply those. And that the square root of x plus 7 times the square root of x plus 7 is like squaring a square root, so I'm going to end up with x plus 7. The square root of x plus 7 times the square root of x plus 16 is going to give me plus square root of x plus 7, square root of x plus 16. The square root of x plus 16 times the square root of x plus 7 is going to give me another square root of x plus 7, square root of x plus 16. And of course, square root of x plus 16 times the square root of x plus 16 is like squaring that square root. So I'm going to have x plus 16. And that all equals 81. So I'm going to have 2x plus 23 plus 2 times square root of x plus 7 square root of x plus 16. So the issue, compared to the other two times when I squared both sides of the equation, that was enough for me to get rid of the radicals. Here, squaring both sides, I still have terms with radicals in them. So I have to account for that. I got to figure out a way to undo this. So I'm going to subtract 2x from both sides and subtract 23 from both sides. So I'm going to have 2 times the square root of x plus 7, square root of x plus 16, equaling a negative 2x plus 58. Going back to some rules that we learned before, let's divide both sides by 2 because both terms on the right-hand side are also even, so I could do that. So I'm going to have the square root of x plus 7 times the square root of x plus 6. It's going to be negative x plus 29. And recognizing the fact that if I have two separate square roots being multiplied together, I can rewrite that as the square root of their product. There should still be a 16 up here. So we have that. I still have that radical, but now when I square both sides and do a second squaring, the radicals will now finally go away. So sometimes you might have to do more than one squaring. Of course, you have to manipulate it so that as you do it, the radicals will eventually disappear. So for this, I'm going to have that x plus 7 times x plus 16 equaling negative x plus 29 negative x plus 29. And so when I work this out, I'm going to have x squared plus 23x plus whatever 7 times 16 is, 112. Negative x times negative x is x squared. Negative 29x, negative 29x is going to be a minus 58x. And 29 times 29 is going to be 841. So I do have a quadratic equation, but as I go through any steps to try to get anything I need on the same side, I mean, ultimately I want my x squareds on the same side. And when I do that, I'm going to be subtracting x squared from both sides to make that happen. They just disappear. So this becomes more of a linear equation. I'm going to add 58x to both sides. And that's going to give me 81x plus 112 equals 841. Subtracting 112 from both sides, I get 729. And dividing both sides by 81, I get 9. So x equals 9. Now again, I have to be careful as I do this. I'm going to pan out a little bit. I don't want to move that. All of this work I had done, again, was working under the assumption that both of these radicals existed. And for that to be the case, for the first one to work, let's do orange here. For the first radical to work, x had to be greater than or equal to negative 7. And for the second one to work, x had to be greater than or equal to negative 16. I don't have to really say this part here because if x is greater than or equal to negative 7, it has to be greater than or equal to negative 16. So this has to be the case, which 9 falls into that category, so we're good for this. But I always have to make sure to check back to make sure that whatever answer I'm coming up with isn't having some sort of fault with the original functions and isn't producing something that doesn't exist. So that's when we get into example 2 now, or example 3, which we deal with extraneous solutions. So let's have a look at them. Now these are going to pop up some extraneous solutions, but there's different ways to determine them and figure them out. There we go. So A is obviously a rational equation. I want to start this off by saying, okay, well, before I start making determinations about like what are my possible domain restrictions, I'm going to factor anything I could possibly factor, which on the left-hand side, really not much to do. Although I don't want to write a plus sign where there's a minus sign. That would certainly throw me off a bit. So minus 4 times x over x plus 4 equals 32 over x squared minus 16. I don't want to rewrite that. X squared minus 16 is the difference of squares, so that's going to be an x plus 4, x minus 4. It's important to have those because identifying those makes it easy to identify what's going to cause some potential issues. Obviously, if x were to be 4 or negative 4, it's going to make, I mean, each one's going to make 2 of these 3 rational expressions become a quantity over 0. And I can't have that. So I have to work under the premise here that x is not equal to 4 and x is not equal to negative 4. Keeping that in mind now, I'm going to work under the premise that is the case, so I want to carry through the work I need to do to solve this. Now, again, when I'm dealing with rational equations, my goal is to be able to eventually cross-multiply. Can't really cross-multiply here yet because I need to have a single fraction on one side and a single fraction on the other. I have a single fraction on the right-hand side, a single rational expression. On the left-hand side, though, I have the subtraction of 2 rational expressions. So I got to carry through that subtraction, and for that to happen, I have to get common denominators. And under most circumstances, I'm just going to take the 2 denominators I see here and multiply the tops and bottoms by those. I'm kind of squishing it in here. And so the left-hand side is going to become x times x plus 4 over x plus 4 x minus 4 minus 4 times x minus 4 over x plus 4 x minus 4, which equals 32 over x plus 4 x minus 4. So on the left-hand side, I have essentially x squared plus 4x minus 4x plus 16 over x plus 4 x minus 4. And that's me doing several pieces of work all at once. I'm distributing the x here. That gives me the x squared plus 4x. I'm distributing the negative 4 here, the minus 4, so it's negative 4 times x, which is a minus 4x. Negative 4 times negative 4 is a plus 16. I didn't combine any like terms, although if I can, these x's would disappear. So I'm here. Now, as I said, I could just automatically cancel these out because they will. So I essentially just have x squared plus 16 on top. The only way for this to be a true case, now I could do some cross multiplying if I want to. However, if I do cross multiplication and multiply it through, I'm going to have a fourth degree expression on one side of this equation when I do that. Because x squared plus 16 times x plus 4 times x minus 4 is going to give me a fourth degree polynomial, which we haven't gotten into how to solve those yet. So, I don't want to go that route because I don't know how to handle those. But I can also use the fact that I have x squared plus 16 over the same denominator as 32. If they're both being divided by the same thing, that means that the tops have to be equal to each other. So I have to work under the premise now that x squared plus 16 would have to equal 32. Makes sense. And so x squared is going to be 16 when I subtract both sides by 16. And when I square root both sides, remembering the plus or minus here, I get that x equals 4 or x equals negative 4, which unfortunately are the two conditions I said, well, I can't have that happen. Those cannot be the case. Therefore, both of these are extraneous, which implies there is no real solution. So that works out pretty neatly, so for B, now I'm going to show you a couple ways of handling it. One, you can, if you're paying attention, will make it known right away based on something I mentioned before in this video. For me to start going through the process of solving this equation, first of all, I'm going to take note of the fact that A is going to have to be greater than or equal to negative 4, first off. Because that would make the radical portion of this not exist if it didn't meet this condition. So I had to work under that premise. I'm going to subtract 7 from both sides. And I get this. Now at this point, you could stop right here and say no real solution. Because the square root of a plus 4 needs to be greater than or equal to 0. The square root of anything should be positive or 0. Because it's a principal square root. It means only the positive square root. A positive square root's not going to give you a negative value unless you have a non-real answer. I'm not looking for non-real answers. So I could say no real solution right there. But say you didn't notice, say you weren't paying attention, and you didn't notice that you're saying the positive square root of something equals a negative number. You will eventually be able to make the same conclusion as you proceed through this. So let's continue this as if we didn't notice that. I would of course then square both sides to get rid of the radical, and that gives me a plus 4 equals 16, and that means that a would have to be 12. And you're saying, well, wait a second, Mr. Sorrentino, this is a number. It's certainly greater than or equal to negative 4. What's wrong with it? Well, here's what's wrong with it. I'm going to go back to the original equation. I should always be doing this anyway. I should be checking my work on any equation I solve to make sure that the answer I get works. If I do the square root of a, which is now we're saying is 12, plus 4 plus 7, if it's an answer, it should equal 3. Well, 12 plus 4 is 16. The square root of that is 4. Does 4 plus 7 equal 3? Well, no. 4 plus 7 is 11. So that doesn't work. So this is extraneous because it simply doesn't work. That happens very frequently with radical equations as well. I'll get solutions that algebraically are sound, but when I go back and check them, they just don't work. They don't cause a domain restriction or an issue like that. They just don't work. And that's what happens here. So if I only get one solution and I say it's extraneous, that would give me the same realization that there is no real solution. So, there's different ways to come to that conclusion in this type of problem, and that's how you'd go about doing it. The last examples that you have deal with situations that are a little bit more abstract. And all they're asking you to do is solve the equations for the indicated variable. Now here I don't have to worry so much about domain restrictions and things like that because I don't know what any of these are. So we're still working under the premise that these things are all existing, and that these expressions and combinations are existing. But I can't restrict it and say like it's not when it's going to work and not going to work unless I know more about these numbers. So let's have a look at that last example 4. So here we're just looking to solve the equation for an indicated variable. Right now this equation is solved for c. C is alone on one side of this equation. I want to get it so it's solved for b, this one right here. So I got to think about, well, I want this to look like eventually b equals something on this side. That means that b should be alone on one side of this equation in the numerator. So when I look at this, I say, well, what do I need to do to carry this out? I can think of the right-hand side as being c over 1. And that allows me to cross multiply. So I can say that d equals acx plus bcy. At least now I have the variable I want in the numerator. I want this b to be the one that's alone. So I got to think, well, I have a cy being multiplied to it, and cy itself is a multiplication, and I have an acx being added to that b. So if I'm following my order of operations in reverse, I get rid of any additions and subtractions first. So I'm going to subtract acx from both sides. And what that's going to leave me with is I'm going to have D minus ACX equaling B times CY. And I'm writing it this way only because of the fact I want to kind of emphasize the fact that that CY is, in total, is being multiplied to B. And that kind of lets me know what I need to do to get B alone. I need to divide both sides by CY. And what that's going to give me now, because these would cancel, is that B is going to equal D minus ACX over CY. And that's the expression I want to get. For B, I want to solve this for P. I want to get, so basically I want this guy, this one right here, to be alone on one side. So I want P to equal something when all is said and done. So let's work on trying to do this. Well, trying to get P in the numerator right now is a little complicated because right now I have a fraction involving P being added to another fraction. If I try to do anything right now that puts P in the numerator, or I try to combine the terms I have over there, I'm going to start creating more variable P's, and I certainly don't want to do that because that goes in the opposite direction. I mean, I don't want to create more of the same variable if I'm trying to get it down to just one being left alone. So what I'm going to do to start this one off is I'm going to subtract 1 over m from both sides. And so I have 1 over f, that's a sloppy looking f, minus 1 over m equals 1 over p. When I have variables in the denominator, I try to do some sort of cross multiplication, which I can only do if I have a single fraction on both sides of the equal sign. I have it on the 1 over p side. I have two fractions being subtracted on the other side. So I got to carry through the subtraction, which means I need to establish some common denominators. So I'm going to multiply this one by m over m, and this one by f over f. And what that's going to give me is I'm going to have m over mf minus f over mf equaling 1 over p, which means I'm going to have m minus f over mf equaling 1 over p. I could cross multiply and give myself more work to do, but it stands to reason that since p and 1 over p are reciprocals, then p should equal the reciprocal of this side. So I'm going to have mf over m minus f, and that solves the equation for p. And that's the end of it. So that's all I have for this video. If you have any further questions, please make sure to bring them up in class and ask about it. Until next time, have a good day.